Have you ever stopped to wonder where our best engineering ideas really come from? I mean, what if I told you that the blueprints for the next big thing weren't tucked away in some high-tech lab, but were actually hiding in plain sight right outside your door? Yeah, let's get into it.
All right, here's our game plan. We're going to go on a little journey to uncover some of nature's most amazing engineering secrets. We'll start with the big idea, this hidden genius. Then we'll dive into 2 incredible case studies. After that, we'll see how these wild ideas can be turned into real-world machines. And finally, we'll look at the master blueprint nature has left for us all. So this hidden genius, what is it? Well, you can think of it like the planet's own research and development lab. One that's been running tests, iterating, and perfecting designs for literally millions of years.
It's constantly tackling the big questions. You know, like, how do you build something that's super strong but also flexible? Or, how do you design a grip that can hold on forever without ever getting tired? It turns out nature has already cracked these problems. The solutions are all around us. We just have to know where to look.
And this whole practice, it actually has a name, biomimicry. It's a simple but really profound idea. Basically, you look to nature's time-tested designs to solve our own modern challenges. I mean, why try to reinvent the wheel when evolution has already spent eons perfecting it, right? It just reframes nature as the ultimate inventor. So let's get into our first case study, the tree fern. Now, at a glance, you'd probably think, yep, that's a tree. But if you look closer, it's a total masterpiece of structural engineering that completely breaks the rules. Okay, so a normal tree, right? It makes a solid, wooden trunk, and it gets wider and wider as it gets taller. The tree fern, it does something totally different. Get this. It has no wood at all. Instead, its trunk is this incredible bundle of fibrous roots all twisted and wrapped together. It's like building a skyscraper not with giant concrete pillars, but with thousands of interwoven steel cables. That's how it gets its height and stability, all through flexible strength.
And the genius design doesn't stop with the trunk. Its leaves, the fronds, are fractal, meaning the same pattern repeats at smaller and smaller scales. It reproduces using spores, no need for flowers or seeds. And because all the new growth happens right at the top, you can actually transplant them pretty easily. And this isn't some newfangled design either. These things have been around since the Jurassic period.
One of the most beautiful things about it is this elegant mechanical trick for how a new leaf grows. It doesn't just sprout. It starts out as this tight little coil called a fiddlehead. And this shape is brilliant because it keeps the super delicate growing tip protected right in the center. Then it just slowly unrolls, revealing its full structure. It's a simple, perfect mechanical solution.
Okay, so we've seen structural integrity. Now let's switch gears to mechanical efficiency. And for that, we're going to look at the bat. The question is simple. How in the world can a bat hang upside down for months during hibernation without using a single drop of energy?
And if you want to know just how crazy this mechanism is, get a load of this quote. The locking mechanism is so passive, so purely based on physics and not muscle, that it stays locked even after the animal has died. I mean, that's not just efficient engineering, that's kind of eerie and absolutely brilliant.
So how does this thing work? It's a beautifully simple 3-step system, and it's all powered by gravity. First, the bat's own body weight pulls on a tendon in its foot. That pull causes the tendon to slide through a special sheath that has these little ridges inside it. As it pulls, the sheath tightens and those ridges grip onto the tendon, locking it solid. No muscle, no effort, just pure, clever physics. And the advantage here is just massive. This whole system, the tendon locking mechanism, or TLM, it lets the bat just hang out for incredible amounts of time without burning a single calorie to maintain its grip. It is the absolute ultimate low-energy solution, totally perfected by evolution.
Okay, so we've got these incredible natural designs. The tree fern, the bat's claw, that's great. But how do we actually get from a bat's foot to a piece of technology we can use? Well, the next step is to translate that biology piece by piece into engineering.
And the translation is amazingly direct. It's almost one-to-one. The bat's tendon, that becomes a high-tech cord we call a flexor line. The ridged sheath that does the gripping, that's engineered into a new sheath with a special notch. And the bone and claw that provide the overall structure, that just becomes a metal main bar. We are literally taking the biological parts list and building an engineered version.
So here's how our new gadget works. First, you just insert the mount into a hole. Then, you pull on that flexor line, which bends the mount so it presses against the inside. And just like the bat's body weight, that simple pulling force locks the entire device securely in place. To get it out, you just let go. The force is gone and the mechanism loosens. It's a perfect, reversible anchor copied straight from nature's playbook.
So let's pull all this together. When we look at these amazing designs in the wild, what's the bigger blueprint? What are the key lessons we can actually take away from all this?
Well, when you look closely, nature starts to reveal its core design principles. The tree fern teaches us about strength in numbers, using lots of small, fibrous parts to create flexible, resilient support. The bat shows us the absolute magic of passive locking, designing things that hold tight without needing constant power. And both of them are just beautiful examples of elegant mechanics, where simple physics creates incredibly sophisticated results. The ultimate lesson through all of it, efficiency is king. Evolution will always, always find the lowest energy way to get a job done.
And that kind of leads to one final thought. We've just talked about a fern and a bat, but this level of genius is literally everywhere. It really makes you wonder, what other incredible million-year-old solutions are out there, just waiting for us to finally notice them? The blueprint is in the wild. All we have to do is learn how to read it.